Okay, so let's continue our discussion of the LIGO experiment and the generation of gravity waves and their detection. So here we'll make a model of a binary star system that generates the gravitational wave. Okay, it's be very naive. Okay, well, I'll have a couple of masses, m1 and m2, orbiting one another with a distance r between them. So r is the distance between them, and remember that variable z is very large, the distance to the detector. Okay, and so I'll imagine a terribly simple kinematics here where they rotate around one another. The center of mass is at the origin here. R1 reaches to M1 and R2 reaches to M2, and they're orbiting one another with a frequency I call nu suborbit. Okay, and that'll just be my model of the antenna, the source. Like when I'm doing electromagnetic waves, I take a simple antenna or a simple configuration of currents, okay, or of charges which are accelerating, or dipole which is rotating, okay, or something like that, and I generate my electromagnetic wave, and then I study it. I take the same approach here, right? So I'm not worrying about complete self-consistency. I'm just making a model of a source. Okay, I'm not worrying that in real life, of course, this force between them would be generated by space-time curvature. I'm just going to put it in by hand and look at the output very far away, the gravitational wave very far away, and that'll be fine. And then, of course, the professionals that come in with the full Einstein equations and the full consistency between the motion of the mass points and the generation of the waves do better. Okay, I'll try to be consistent, and I'll do it by hand. So we'll apply Newtonian mechanics to the binary pair. So the energy is I just do an exercise in Newtonian mechanics. See that the binding energy of the two guys, they're bound gravitationally, just minus g m1 m2 over 2r. Okay, the 1/2 is the binding factor. And just derive that as a simple exercise in Newtonian mechanics. It's done in the textbook, or just look it up. Now the masses are accelerating, and so they're radiating, okay, and they carry off energy at a certain rate, and a calculation of that rate gives this as a result. Okay, the rate at which energy is leaving, that's the rate at which the binding the energy bound in the system is diminishing. Okay, minus energy is leaving. Okay, goes like this in this formula: g to the 4th, 1 over c to the 5th, 1 over the distance between the points to the 5th, and then factors of n. So energy is being radiated away. If energy is being radiated away, r is decreasing, and eventually m1 and m2 emerge. From this equation, giving me the dependence of the binding energy on the distance between them. Okay, I can plug that in and get the rate of change of the distance between them, and there you go. These are important formulas, okay, because of as discussed in the textbook, the deterioration of the distance between members of a binary system were studied and observed long before LIGO, and it was found that in a particular case of a particular binary, that the formulas and the hypothesis that energy is being lost in gravitational waves fit the data. Okay, it described the rate of change of the distance between the binaries, and was quite a wonderful success, which also won a Nobel Prize for the experimenters that made those observations. Okay, so take a look at the textbook. It goes through the numbers of that famous set of experiments. Okay, and it cites the experiments and gives you the details of them. And it's interesting to do that as an exercise in getting used to these various formulas. But you see, it's quite simple. It's quite naive. I steal a formula for energy carried by gravitational waves. That's not so easy, but it's not so far beyond what we can do in this pre-field theory course. Okay. So we'll be seeing that the gravity wave at LIGO is given by a formula like this, okay, going like g squared m1 m2, falling off like 1 upon z. That's the distance from the source to the sink. It falls off as 1 upon r. We've seen that already, a factor of 1 over c to the fourth. And then there's a cosine of of the frequency of the gravity wave, and it's propagating in the z direction as an ordinary wave. And we'll see that the frequency of the gravity wave is twice the frequency of the orbital motion. Right? The orbital motion, I'd label one of the stars A and the other star B, and have a vector going from A to B, and it rotates at a certain rate, new orbit. Okay, okay, and the rate at which the characteristic frequency of the gravity wave is twice that. Okay. Okay, and we'll see that in a minute. And of course, it's not surprising to us. We already know that if you have a system which is rotating and accelerating, that the quadrupole moment, of course, rotates twice. Each time the planets rotate once around each other, and that factor of 2 is just the factor of 2 that comes into the quadrupole moment, and it's there in electromagnetic radiation, and it's here as well. It's there in tides. You have 2 high tides and 2 low tides every day, dictated by the rotation of the Earth under the moon. Okay. The Newtonian prediction for new orbit comes from Kepler's laws, and okay, we can go back to our simple model for the binary and derive this, or just look it up as one of Kepler's laws. That if I know what g is, I know the mass of the system, I know the distance between them, then I know the frequency. It's just one of Kepler's laws. Remember it? It's the one that says that the frequency squared goes like 1 over the distance cubed over the major axis of the Earth to the cube, and I'm doing a circular orbit, so it's simple. Okay, LIGO is sensitive to frequencies in this range, and so the frequency of the gravitational wave twice orbit should be in this range, and it is. Okay, let's recall the wave equation for h bar. We had it written here, and it was simplified for the fact that we're far away from a source which is localized, and so the 1 upon distance can be pulled outside, as shown there. Okay. So what I have to do then is to do this integral, okay, for a simple source, and my simple source is just these 2 orbiting masses, m1, m2, one at this point and one at that point, rotating around with a new orbit of, I'll call it omega over 2 pi, frequency related to angular frequency that way. Okay, so number 1 is orbiting like this, okay, in the transverse direction, just rotating around. I'm taking the model, have no z extension, it's just rotating around in xy direction, and then the position of the other one is just given by putting the appropriate minus signs in here, changing R1 to R2, and rotating with the same frequency, of course, because that's how they're going. Okay, so then my energy momentum tensor, okay, for point particles is just m v times v, m2, v times v, okay, with the indices as shown here, where this is the velocity of my first particle, and here's the velocity of the second particle, and here's the mass of it. Okay, now m1 is its mass density is localized, okay, at x1, x2, and it's in the z-plane, and similarly for m2. So you see the integral over the mass densities is done by the delta functions. There's nothing there, nothing to be done at all. The delta functions just tell you your mass points, okay, at those positions, okay. So that's done immediately, and then so I just plug into this formula here the velocities for x1 and x2. The velocities, it's non-relativistic kinematics, so I take the time derivative of this fellow, the cosine becomes a sine, I get out a factor of omega, okay, and so I have 2 of those factors, So T11 omega squared cosine squared, okay? And then I can write that as cosine of twice omega like that, because I want to write it as a cosine, not a apparent nonlinear object. And then T12 is equal to T21, okay? Okay, so I just put in 1, 2 here, 1, 2 here, okay? So x component here, y component here, and then similarly over there, okay? And so I accumulate all these pieces. Let's see, when I did this calculation, because I had the two terms, so I had an M1 term, okay, with a R1 squared, and then I had an M2 with R2 squared. So I pulled out a moment of inertia, okay, for the binary system. That came out of my arithmetic, okay? And similarly over here, it comes out of my arithmetic. It goes like omega squared, a cosine times a sine, okay, as you see, okay, as you see from my arithmetic, okay? And so that's sine of twice omega with a factor of half, and then T22 similar to the case over there. Okay. Now I'm only interested here in the time-dependent pieces of Tij, so I drop the constants. I'm looking for radiation time dependence in my pattern, so I put that in here like this. And here's T11, T11, T12, and T22. Okay, and so my H bar then is just, here it is. Okay, I evaluated it at T minus Z over C. It's a traveling wave. That's my formula. Okay, I see that the strengths of my wave go like these moments of inertia. Okay, I get omega squares up here. Okay, and so there's my gravity wave. I see in particular, if I'm looking at my plus polarization, okay, that T11 indeed is minus T22. Okay. So that the polarization states coming from the source match the plus polarization and the cross polarization that I expect of a gravity wave. Okay, that's just built into the formulas. It's the quadrupole moment. Okay, that's radiating. Okay, and then the polarization state simply inherits those polarization states. Okay, and so it satisfies the transverse traceless condition of the polarized gravitational waves. Okay, that's good. I also see that the angular frequency of the gravity wave is twice the angular frequency of the binary. Okay, that was built in, right? Because of the two omegas, right? It was a quadrupole moment that's radiating. Okay, that's quadratic, and the quadratic dependence gave me cosine squared, sine squares, or sine times cosines, which are then cosine 2 omega, sine 2 omega, or cosine 2 omega. So twice the angular frequency of the orbital motion is the characteristic frequency of the quadrupole moment. The quadrupole moment rotates twice around as the binary make one orbit, and so that's what's recorded there. Quadrupole moment of the binaries radiate. That's what it says. The gravity wave propagates tidal forces. Okay, and that's what we have. We have the correct order of magnitude. We have the correct z dependence. We have the correct traveling wave dependence. We have the correct polarization dependence. We really have done quite a lot in the direction of the LIGO experiment. But of course, there's a lot more to be done as well. We've taken special geometries. I'm not going to spend time on geometry, but the pros have to do much more general calculations, and hats off to them. Okay, I remind you, on August 17th, 2017, LIGO observed merging neutron stars, and that was particularly interesting. Neutron stars are not quite black holes. They're not quite massive enough for it, so they don't have event horizons. Okay, so when they smack against one another, and those neutrons suffer, accelerations and such, they radiate electromagnetically very, very well, and that's what is observed by the telescopes that complement the observations of the LIGO gravity detectors. Okay, so that's all I want to say about gravity waves. Let's go back now and discuss some general principles of special relativity and general relativity. Say a few words about the cosmological constant and dark energy. Okay, and look to the future. Okay, and we'll do that next time.